Olá, boa tarde a todos. É um grande prazer estar aqui com o Rodrigo, professor Rodrigo Sacahui, que é um amigo também que eu fiz quando estava lá em São José dos Campos. O professor Rodrigo, ele é professor titular da Universidade de São Carlos, da Guatemala. Ele obteve o mestrado e o doutorado no Instituto de Astronomia da Universidade Nacional Autônoma do México e fez um pós-doutorado lá no INPE, né, no Instituto Nacional de Pesquisas Espaciais, trabalhando com o professor João Braga. Ele trabalha na modelagem dos blazers, né, dos Gammaray blazers e dos Gammaray busters. E ele é membro da Academia de Ciência da Guatemala, presidente da Associação de Física da Guatemala também, e presidente da Alpha 100, que é um grupo de astrofísica da América Central e do Caribe. Rodrigo, é um prazer enorme ter você aqui com a gente para contar aí um pouco do seu trabalho, que é um trabalho muito bonito. Muito obrigada mesmo. O Rodrigo, ele fala português muito bem, a gente só fala em português o tempo todo, ele me escreve no WhatsApp em português, mas ele disse que vai preferir falar em inglês a palestra hoje. Mas os alunos, se tiverem vergonha de mandar perguntas, podem mandar em português sem problema nenhum, tá bom? Rodrigo, muito obrigada, passo a palavra para você e compartilho a tela sua aqui também, tá?
Então, obrigado, Diana, muito obrigado pelo convite. É um prazer para mim conversar com vocês, para o pessoal do Observatório do Valongo. Assim como a Diana falou, eu tento falar português, mas acho que se inicio falando português, vou mudar para o espanhol e vou continuar em espanhol e vou ficar falando espanhol a palestra toda. Meu inglês também não é bom, mas acho que é melhor com o meu português. Mas, de novo, muito obrigado, Diana. Um prazer estar com vocês e vou falar um pouco do trabalho, nosso trabalho. Particularmente, eu decidi apresentar o trabalho do Blazar, porque aqui colaboro com o pessoal que eu conheci no INPE, a Ana e o Manu. Então, thank you, Diana. So I will start. I will switch to English, but feel free to ask in Portuguese. I will try. I am sure I have not forgotten all my Portuguese, but for sure I have forgotten a lot. So today I will speak a little bit about gamma ray activity of blazars and some possible implications for tera-electron-volt neutrinos that has been detected by IceCube and by other, and in the future we hope that by other experiments. So this is a work in collaboration with Anna from Argentina, Antonio from Italy, Ankur in Sweden, Manuel in Brazil, and two former students of mine in Guatemala that now are abroad, Mabel in Mexico and Anthony in Argentina too. So the outline of my talk, I will start speaking a little bit of generalities of lasers, of HGNs, how we decide. After I will speak a little bit about how we decided the sample to work on, and a little bit of the gamma ray observations, then about the duty cycle, one parameter that is quite important in this work, then the connection between this gamma ray emission and the neutrino expectation, considering one leptohadronic model, and then my conclusions. So just to start, blazars are one kind of active galactic nuclei, which are galaxies that their center is quite bright, it's really bright. So if you look far away, you mostly will detect their center. The center is the central 1 parsec cubic, and it's around 10 to the 4th times brighter when comparison with a normal galaxy. So these active galactic nuclei have been widely studied because they are observed at all the wavelengths. Their peak in intensity is at radio, so the trigger or the study of these subjects was triggered with the radio astronomy development in the 70s, 80s, They are quite exciting objects because here you are watching really extreme physics. The actual model proposed that an active galactic nuclei is composed in the center by a supermassive black hole, or several black holes, but it has a compact object, really heavy, so it must be a massive black hole with masses from 10 to the 6 to 10 to the 10 solar masses. Around the black hole, we expect an accretion disk formed by particle and dust and radiation. Also, a torus of dust and gas, which is like around light years from the center. And finally, we also have detected relativistic jets that goes out from the center in perpendicular to the plane, to the accretion disk. And in this plot, I showed to you one of the most famous active galactic nuclei, the 3C279, which is a quasar or FSRQ blazar, which has been really interesting to study because it's really variable in several wavelengths, ranging from gamma rays to radio to optical. Also, some polarization studies have been made. So these kind of objects are really, really exciting to work on. But today I will focus on one kind of these active galactic nuclei, which are called blazars, which are the most variable and luminous type of AGNs. They emit from non-thermal process. I mean, we detect non-thermal electromagnetic emission in all observable bands. There are two types, the BLLAX and FSRQ, which presents different observational properties, but still the separation is not that strong. I mean, it is not so easy to differentiate BLLAX from FSRQ. The most important observational difference is that FSRQ present observational lines. Meanwhile, BLLAX doesn't present these observational lines. And one important thing is that the actual model proposed that the different kinds of AGNs are because we are observing these objects from different orientation angles. I mean, if we look in horizontal observational line, considered to what this object, we will detect a radio galaxy. Meanwhile, blazars are when the relativistic jet is aligned with our line of sight. It means that in blazars, we are detecting mostly the activity of the jets. So that's why when we study blazars, we are studying the activity of the jet. And this is a typical spectral distribution from this object. It is named the two-bump set. The first bump, the first bump is proposed to be explained by synchrotron emission. Synchrotron emission is produced when relativistic electrons are accelerated in the presence of magnetic fields. And the second bump is not quite clear, but a model proposed that this could be inverse Compton from the same relativistic electron that produce synchrotron. It could be also produced by cascades, but proton interactions in the jet. Also, another models proposed that this could be a combination between these two processes, and also synchrotron from heavier particles like protons and nucleus inside the jet. And this is the spectral energy distribution called the two-bump, and this one is called the synchrotron peak, and the other one is called the inverse Compton peak. I highlight this because we found an interesting thing in these blazars related to this synchrotron peak. The synchrotron peak is in low energies, and it goes from radio to optical X-ray. And where the peak is located is sometimes used to classify these blazars. I mean, high synchrotron peak, medium synchrotron peak, and low synchrotron peak. So a little bit more about blazars. These are the most active extragalactic gamma ray sources. I mean, these sources are really, really bright in gamma rays. Also, they present gamma ray variability in several scales. It can range from days to years, even hours, depending on the capability of the detector, but they are really, really variable sources. They are actually strong candidates to produce these high-energy cosmic rays and these high-energy neutrinos. That's why we started this work in collaboration with friends in Italy. And they have been observed up to energies of higher than tera electron volts. This is one of the most famous Blazar, Markarian 421, which is one of the closest blazars detected, and it has been observed also in radio, in optical, in gamma rays, and in even high energy gamma rays, I mean tera electron volts. For this study, we use data from the Fermi Gamma Ray Space Telescope. This telescope was launched in 2008, and it is still working. It's really a really great experiment. Because of its properties, it actually started a new era in Blazar studies, because now we have a great detector in space. It is composed by two instruments, the GVM, which is mostly used for gamma ray burst studies. It is for spectroscopy of gamma ray burst, and the Large Aperture Telescope, LAT, which is a pair conversion tracker, which is actually the instrument that we use for this study. The LAT specifications are that it detects photons in the energy range between 20 mega electron volts up to 300 giga electron volts. I mean, this is the optimal energy range, but you can go further and to lower and higher energies. It has a field light, a high field of view, which is important because we want to monitor the sky. Fermi-LAT is orbiting our planet, and within 3.2 hours, LAT covers the full sky. That means that we can have a picture of the full sky every 3.2 hours, which is good when we are monitoring sources like this continuous, like blazars. The angular resolution is not so good, but for this kind of studies, for gamma ray astronomy is quite good. I mean, it's quite a great improvement from the previous mission, the BATSI detector, which was launched decades before. But this is a really great improvement in gamma ray astronomy, and it has given a lot of achievements in gamma ray astronomy. In particular, we will focus on the Fermi Gamma Ray AGN catalog, the 4LAC, which was made using 8 years of data. With these 8 years of data, around 3,000 AGN sources have been detected, which are distributed in all the sky. I mean, there is an isotropical distribution in their location in the sky. From these AGNs, 98% are of the Blazar type, so that means blazars are actually the most common gamma ray source in this energy range. So if we watch the sky in gamma rays, what you see are blazars mostly. From these blazars, 24% are cataloged at flat spectrum radio quiet. The other 38% are cataloged at BL-LACs, which names is after the first detected of this kind with the BL Lacertae blazar. And finally, 38% are still not categorized between these two types of lasers, so they are known as unknown type of lasers. Because, as I said before, because BL-LACs doesn't present spectral lines, it's actually hard to know the redshift. It's actually hard to detect other wavelength properties to qualify these objects and to differentiate between these two. And this is the 4th AGN LAT catalog, which has been important for gamma ray astronomy because we have learned a lot. I mean, there have been studies about these two populations, these two kinds of LLACs and FSRQ, to try to understand which are the difference and why we have these two types. I mean, some authors propose that VLLACs are evolving to FSRQ. Others propose that it has to be also with another observational properties, but still we are advancing in this differentiation. Also, we have been able to make individual source studies, mostly in the multi-frequency era in which we are. It is really important to cover all the spectra from these sources. We can contribute, I mean, the gamma ray astronomy contributes a lot in this part, and also it is important because now in the era of also of gravitational waves and neutrino astronomy and cosmic ray astronomy. Also, there had been studies of timing correlations between gamma ray and other bands, and more particular, we have been studying correlation between gamma rays and optical, and trying to understand, as I said before, these two bump spectra, if we can differentiate that the origin is leptonic of leptovadronic, of a mixture of those, of it is one zone emission or two zone emission. This type of studies are really necessary, so there have been several correlation studies between gamma rays and other bands. Also, as I mentioned before, a possible link between gamma rays, AGNs, and ultra-high energy cosmic ray detected most by Pierre Auger. So it is important. We still have no certainty about this origin of these high energy cosmic rays. Also, proofs for extragalactic background, also the ponderation of how much is the contribution of AGNs in the extragalactic background light. And finally, two lines that I will present a little bit here is the AGNs activity, how active these sources are. It means how many material they have to accrete, and also how is the possible relation of these objects and the astrophysical neutrinos detected by the IceCube collaboration. So for this work, we used a small sample. We selected 38 blazars, 19 of the VLLAC type and 19 of the FSRQ type. Actually, this number was limited mostly because of the computational time that takes to reduce the data, and also because we wanted good statistics, so that's why we selected the high flux in gamma ray band. I mean, these blazars have high flux in gamma ray band. That was two of our criteria to select the subjects. From this sample, we have a wide range of redshift, but of course they are mostly near blazars. Also, it is because we don't expect to detect faraway blazars, mostly because of the AVL contribution. I mean, in the path from the source to Earth, these gamma rays are absorbed with interactions with the infrared background or even with the cosmic ray background, so we don't expect to detect faraway blazars. And from these 19, 2 have not reported redshift. And here you can see the sky map distribution. They are randomly distributed in the sky, and also the redshift distribution, where we can see that most of our sample is between 0 and 0.5 in redshift. I mean, they are nearby galactic objects. They are nearby extragalactic objects, sorry. So about the gamma ray observation, as I mentioned before, we use data from Fermilab, which is public. We obtained gamma ray light curves for 10 years of data, considering energy between 0.1 and 300 giga-electron volts, and considering a region of interest of 15 degrees. We also considered this EVL absorption, as I mentioned, the gamma ray that goes out from the source, not the same flux that reaches Earth, because the gamma rays are being absorbed in their path from the source to Earth. So we consider the Franceschini model for this absorption, which is one of the most used in literature. And for the reduction of the data, we use the Fermi science tools. We also considered the isotropic and galactic diffuse emission components. And after trying several binning time, we decided to use 2-week temporal binnings. I mean, this means that each point of this plot is the data reduced for 2 weeks of observation. We decided 2 weeks because it gives the best resolution in temporal, and we don't have so many upper limits because if we use a smaller temporal binning, I mean like 1 week or 3 days, we used to have several upper limits, which is not good for this statistical study. So that's why we decided a 2-week temporal binning. And I mean, when I told you that most of the study was limited also with the computational time, because the reduction of one of these light cube takes around, well, in a normal computer, it took about 3 days. So reducing for the object, it was a little bit, it took us a lot of time. So it is not so straightforward to see or to decide or to discriminate how much is the activity of these sources. So we included this duty cycle parameter, which is actually the time that the source spends in an active state when compared to the total observational time. But the most difficult part, or I mean the hardest part, is to define what we can take as an active state, as an active state episode in the sources. So we followed the work done by Patricelli et al. 2014, which converts the DC parameter in terms of observables that are the average flux, the average flare flux, and the baseline flux. The baseline flux will be like the flux in which the source is in a steady state. Is the steady state flux of the source. The average flare flux is the average flux of when the source is in active state, in flaring state or active state, and the average flux is the average flux of all the observational time. In this case, the average flux of the 10 years of observations of Fermi-lab data of the sources. So it can be converted using simple mathematics to this other expression of duty cycle. And as I mentioned, the approach, or I mean, the criteria to decide how to differentiate steady state from flaring state is not that straightforward. But for that, we follow with the criteria proposed by Tluxicon et al. 2010. And basically, what Tluxicon proposed is that the steady state activity of the Blazar is well characterized with a normal Gaussian distribution. Meanwhile, the active state is described by a log normal distribution. So what we did is actually we created a histogram of flux and the number of events that, I mean, the number of times that the source present that flux quantity. And with that, we fit these two functions, and we detected, selected, I mean, I don't know which word to use, but I mean, we could differentiate the steady state characterized with the Gaussian function from the active state characterized with the log normal function. And with this criteria, the baseline value, the mean baseline value, will actually just be the ponderate value, the mean value, with from this distribution, from this both distribution. I mean, and also the same for the flaring distribution. We obtained that when obtaining the mean value from the log normal, and with a common fit, we could obtain the parameters that described both quantities. So this was the way that we use to differentiate baseline flux from flaring state flux. So with that, we obtained the duty cycle following the expression presented before. And actually, we don't get one single value because the baseline can vary from 0, I mean, which is the ideal case. The ideal case is when the source is not emitting at all. So the baseline flux will be ideally 0. And it goes to the center of the Gaussian. This is how this is the range proposed for the baseline from this work of Tluxicon. And that means also that the active state threshold, I mean the threshold that differentiate baseline from active state, it's also a range that it goes from baseline plus 3 standard deviation of the Gaussian. So it means that it starts from 0 to 3 standard, from 0 plus 3 standard deviation of the Gaussian, and it ends from the center of the Gaussian to plus 3 standard deviation. I mean, that's where it starts. And the highest flux of this active state is actually the highest flow detected from the source. So with this into account, taking this into account, we have a range of duty cycle that from every source. So that's what we obtained. And for instance, for Markarian 421, we obtained a range between around 10 to 38, I think, which is inconsistent with other works made in the same energy range, but also in difference range, which could mean that Markarian has an activity that is the same at different wavelengths. I mean, at different gamma ray wavelengths, because one study was using Fermi data, and the other one was using Milagro data, which was an Cherenkov water detector that was at Los Alamos, but it was the previous experiment of the Hawk experiment that is working now. So about the general results of the sample, we obtained that the majority of the mean value of the duty cycle obtained for all the sources is around 23. So that means that at around 1/4 of their time, these sources tends to be in active state. The minimum value was 8.3, which is a quiet source, and the highest value, which is actually the Vele Lacertae Blazar, presents a duty cycle of around 45, which means that it is active in almost half of these 10 years of observations. Also, we did the same analysis considering the Vele absorption, not TBL, and the values doesn't change a lot, meaning that the Vele absorption in this energy range is not so important. So what we found is that actually these objects are not so active, which could be important for further conclusions that I would like to present in the next slides. But because we had the sample, we decided to explore another possible correlations, and we found another interesting results. For instance, previous works from Frosati et al. In 98, Kubo et al. In 98, Donato et al. In 2001, reported an anticorrelation between synchrotron peak, the first peak of the set distribution of lasers, and the volumetric luminosity. These previous works were done using radio data from radio telescopes, but we found out that this trend is also present when we use gamma ray luminosity. I mean, this Blazar sequence, this is the called Blazar sequence, which is an anticorrelation between luminosity and this synchrotron peak, which has been observational reported previously, but still has been theoretical explained. I mean, there are some proposals, but still it is still an open question about this trend, and we found this. So this is interesting to see that this anticorrelation also extends to gamma ray energy range, to gamma ray observations. Then we also found no relations between different values. I mean, the duty cycle seemed to be not correlated with the major flare duration. It is also not correlating with luminosity. And also we find no correlation between the duty cycle and the redshift. Of course, this is a small sample. Further works needs to be done. But at least it doesn't seem to be a correlation between these parameters. Another issue I wanted to point out here is that also the FSRQ object seems to be more luminous when compared to the LLAX, and also there seems to have a lower synchrotron peak, which is interesting, and it could be used further to this can contribute to the differentiation between these two kinds of objects. So I will talk a little bit about this possible relation between blazars and neutrino. I mean, recently, I mean, not so long ago, the first neutrino event detected by IceCube and reported with a counterpart in other energy range was reported. It was the IC 170922A, which is a neutrino detected on the 22nd of September of 2017, that was in coincidence with a flaring state of this blazar TXS 0506 plus 056, which is in the same position in the sky of the point where the neutrino was detected. So this is the first coincidence between a neutrino event and a gamma ray flaring event. Also, this flaring event was later reported to be detected not only by Fermi, it also was reported to be detected by MAGIC, a Cherenkov telescope that detects energies, higher energies, but this was the first event in correlation between neutrino and electromagnetic emission. So this was really exciting. And also, this source had a particularity. In 2014, also, an excess in the neutrino flux was detected from the same point, from the same point in the sky where this source is present. So it is an interesting source to analyze, to study. It has reported the first coincidence between neutrino and gamma ray flaring state. Also, a neutrino excess seems to come from this point of the sky. And it is exciting to see that. So with that in mind, we decided to study why is this blazar so peculiar, why it is different from the others, it is not so different, why this blazar, why this? So with that in mind, we started a study selecting the blazars that are in spatial coincidence with the neutrinos detected by IceCube with energy higher than 200 electron volts. So what we did is actually selected the location in the sky of the neutrino. Then we put a restriction that the spatial coincidence less than 1.3 degrees from that point to select which blazars are are so near to that source. And with that, we found 10 objects that fulfills these qualities. And also we made a simple probability study about how probable is that this coincidence is just by random position in the skies. And we found out that the probability coincidence is 0.2. That means that just 0.2 of the sources could be randomly located within the position of the neutrino event. So with that in mind, we continue and we started to analyze these blazars. Unfortunately, some of them are not so bright in gamma rays, or we couldn't do great studies because we don't have so many statistics. We have only upper limits, so it was not possible to the study to make great studies for all these 10 sources, but we focused on the fourth, on the sixth that had some good statistics to make some gamma ray analysis. So these are the list of these sources. We have both types, FSRQ and Bailey-Lax. Even TXS 0506 plus 046, the famous neutrino blazar, is cataloged by some authors, but as a Bailey-Lax object, other authors say that it's not so sure. So maybe it could be also a flat spectrum radio quiet. So we also from this we also have a range of redshifts. We have a near blazar 0.25 with redshift 0.25, and also we have a redshift up to 1.47. So we have a range of redshift, but in particular, the best gamma ray data was for these two objects of OP313 and TXS 0506 plus 056. So we started analyzing those two objects. So what we found is, TXS is the famous that they have this neutrino coincidence. But for instance, OP313 has a flaring state, a gamma ray flaring state, but not in temporal coincidence with with the neutrino event detected. I mean, the neutrino event was detected, and several months later, it presented a gamma ray flaring state. So it is another interesting case to follow. But also, this is one of the brightest lasers because it's far, and even though it's far, it's really a bright laser of the sample. So we started with these two, and using this gamma ray data, following a leptohadronic model, we inferred the neutrino liquor. Here we present the expected neutrino liquor. I mean, we have time against flux for neutrino, considering a leptohadronic model that taking into account the gamma ray flux, it predicts the neutrino flux for these events. We did it for these two objects, considering two different K factor. The K factor is just the relation between intensity of gamma ray and intensity of neutrino. I mean, one is that for every gamma ray we expect, I mean, is 1-to-1 gamma ray emission to neutrino emission, and 0.5 is considering that not all gamma ray goes to neutrino production. Is reflected in neutrino production, sorry. So these values were taken from literature, and with that we can see here that in the upper three panels we have different energy, we find different time beams. We have 6 months, 1 year time beam. It means that each point of this is 1 year data of neutrino. Then we have 6 months, each point of this is a 6-month expected flux of neutrino, and we have 1 month. So what we found, interestingly, is that for TXS, considering this leptohadronic model as expected, we see that the neutrino flux is above the threshold of detection of ice cube. This green line is the threshold of detection of ice cube, considering an energy peak of the neutrino distribution of 120 peta-electron volts. And we find out that is consistent with being detected by the ice cube experiment, considering different time beams. Meanwhile, for OP313, which is a bright blazar, as I said, the flux of neutrinos expected, considering this gamma ray intensity, is not high enough to pass the threshold of detection of ice cube. So that means that this could explain why from this source, even though it's a really bright source, we haven't detected a neutrino in coincidence with gamma ray emission. So this is in coincidence. Here we are taking as a neutrino as a gamma ray emission from 0.1 to 100 giga-electron volts. Also, we are considering low opacity for gamma rays. And as I told you, we considered two values of relative intensities between neutrino and gamma ray. But another interesting thing is that the application of the duty cycle of each of these lasers, could also help us understand why we don't detect so many neutrinos from these sources. Here we present the historical SED for TXS 0506 plus 056, which was constructed using the archival SED with the ASDC SED builder tool from institution in Italy. What we see here are observations in different wavelengths, and in particular, these blue triangles are when the source is in active state. I mean, when it's in flaring state, the flux was higher. So this is the points of the flux in higher state, in high state activity of TXS. But when we use this flux, we see that the neutrino flux is this, purple triangle. That is, the circle should be higher, but I don't know, sorry about it. But it's a really high flux, and that's how we could understand why we detect neutrinos in their flaring state. But meanwhile, the the flux expected from neutrino, considering a duty cycle factor, goes to lower values. I mean, this point, this triangle, this purple triangle, will be the expected neutrino flux if the source was always in active state. But as we saw, the source is not always in active state. Actually, most of their time is in quiet state. So if we use this duty cycle factor, I mean, if we use, here we use the range from 0 to 23, we could see that the neutrino flux expected from this source goes to lower values. This could be a possible explanation of why we don't see so many neutrinos, because we have detected so few. And actually, we have detected just one possible candidate in correlation with lasers. So we think that this application of the duty cycle factor could be an important issue to consider when we calculate the expected neutrino flux from this kind of sources. So, and just to finish, what about the other blazars I mentioned? One interesting particular case is this PKS 1454354, which at the year 2008 had a really bright flaring state, but unfortunately IceCube was still not working, was still not fully working at that time. So what we think is that this would be, this was a quite good candidate for a neutrino emission coming from this source, but unfortunately IceCube was not fully working at that time. But if we see that with this, if we follow the gamma ray neutrino relation that we propose following this leptohadronic model, it could mean that this blazar should have emitted a neutrino that could have been detected by the IceCube collaboration in the year 2008. And then the flux have not been so high, so we see that following this model, we won't expect neutrino from the source. Also for GB6, which is a near blazar in coincidence with the neutrino location. But we see also that considering this leptohadronic model, we also don't pass the threshold of detection of IceCube. So this is what we found for these other two sources. And just to finish, taking into account the peculiarities of this small sample, we just plotted here the flare luminosity. I mean, the luminosity in these major flares of these blazars, the flare duration, and the duty cycle in color. And what we see is that these two seems to be a little bit away from the others. And particularly interesting is that is the source TXS0506, which has been the one reported with a correlation between neutrino and gamma ray flaring state. And the other one is the one that had this major flare in the year 2008 that, following this leptohadronic model, it was expected to emit neutrinos in neutrino flux that could be detected with IceCube. Unfortunately, we didn't have IceCube working at that time, but they seem to be a little bit different when compared to the others, and this could hint us a little bit about the peculiarities that the blazars should have to make them possible neutrino emitters. And we think that there are two things to consider. Mostly is the flare duration. The flare should be long-lasting, and also this source should have a high duty cycle, which is expected, of course, because if you have long-lasting active state, of course, the duty cycle value will go higher. So this is another result we found from this work, that there is a possible. Of course, we need a larger sample of this object to see if this trend to be a particular kind of lasers. So just my conclusions are that the gamma ray of emission of laser is mostly dominated by the steady state phase, I mean, most of their time, they are in steady state, at least for this sample. Also, they present a wide range of duty cycle. I mean, they are, we found blazars with around 10% of active state time, compared with others that almost half of their observational time were in active state. Also, we found that the EVL is not so important in this calculation at this redshift. And finally, that within this leptohadronic scenario, the DC value could become relevant for the expected neutrino emissions from these blazars. So, muito obrigado pelo convite, Diana. And I leave here my email in case you want to contact us, and also you can follow. We are just starting astronomy research in Guatemala, and if you want to follow what we are doing, please go to that link. So, obrigado, Diana. And I hope
Nada, Rodrigo, eu que agradeço muito a você. We have question here.
Okay, go ahead, no problem.
Denise asked about the difference between flares and duty cycle.
Okay, so flares is just a small, it's just the time, I mean, it's the episode where the blazar is in active state. I mean, it's just one episode. I mean, a flare could start today and end in 1 week. The duty cycle is the radio of time. I mean, it will be the number of flares multiplied by the time of each flares when compared to all the total time of observation. So it's a percentage. I mean, that's the difference. A flare is just an active state, and the duty cycle is the time that the source spent in active states, considering many flares, not just one. I don't know if that will be a good answer, but I hope so.
Another question. How the change of models would affect the results and the conclusions?
Yeah, of course, they will affect. We use this one because we expect that of course, that it has to be hadronic. It has to be a part of a hadronic model, because if not, we wouldn't expect neutrinos coming from that source. But also because of observation in other energy bands, we need to explain that as leptonic emission, for instance, radio, X-rays, and gamma rays. That's why we decided to use this one. There are other models, but unfortunately now we just have one case of a study, which is one blazar. So up to now, our models are limited to just one case of study, but for sure with time, with more observations, with more detection of neutrino, I mean, there is, for sure we need a full-scale network of neutrino observatories. There is IceCube and Antares, but there is a few, but of course we will need further observational data to conclude which model is preferred. Up to now, we just have one case, so that's what limits, but that's what made us use this model actually.
Rodrigo, muitas pessoas aqui no chat estão... It's very strange to speak English with Rodrigo.
Imagina, Diana, se você deseja, a gente pode mudar para o português.
Parece que eu não... Se eu falar, parece que eu não estou agradecendo direito, se eu for falar em inglês.
Tá bom.
Olha, muita gente agradecendo a palestra, dizendo que foi ótima a palestra, então... Deixo aqui também o meu agradecimento. Muitas graças, Rodrigo.
Obrigado, Diana. Sou eu quem agradece.
Agradeço muito a você.
Tenho que voltar para o Brasil. Vou visitar o Valongo daqui a pouco.
Sim, será muito bem-vindo se você vier aí nos visitar. Eu tenho certeza que será bom para todo mundo, para você e para a gente também, esse intercâmbio, né?
Obrigado, Diana. Também bem-vindo sempre na Guatemala.
Olha... Qualquer dia eu vou. Muito obrigada mesmo, tá, Rodrigo?
Tchau.
Então, vou fechar.
Até mais.
Até mais. Tchau, tchau.